All right, this is the video for chapter 20. I'm going to go through the entirety of this recitation sheet, but what I would do is only pay attention to the content that is covered in class on Tuesday. Is it the 18th, I believe? Tuesday the 18th. That'll be the stuff that'll actually be on your exam. Feel more than welcome to pay attention to the rest of it. It will be relevant for the final, so that could show up then. But as far as what's on your exam on Thursday, I believe the 20th, that's going to be based on what's actually covered in class on Tuesday the 18th. Let's go ahead and go through. I'll start off with the saponification or basic catalyzed hydrolysis of methyl butanoate. So what happens here, right? Hydroxide, it's a base, it's a nucleophile. What's going to happen is one of these lone pairs is going to attack this carbon center, nucleophile, form that tetrahedral intermediate. So what that looks like is this. We have an alkoxide, we have an OH. And again, basic conditions, you shouldn't have anything overly protonated, you shouldn't have a bunch of positive charges. Everything should either be neutral or negatively charged. And that's what we have right here. So what we're going to have here is this. One of these lone pairs is going to kick down and reform the double bond. But this time, rather than kicking off an OH, we're going to kick off an OCH3. So we're going to lose CH3O, a methoxide anion, right? And what that forms then is a carboxylic acid. What's the name? Butanoic acid, right? 4 carbons in a straight chain. So we're not done yet though, right? Because we're in basic conditions. Because we're in basic conditions, we know that the pKa of carboxylic acids are roughly in the upper 4s, which means in basic conditions, they're going to be deprotonated. And you'll see in biochemistry, at physiological pH, carboxylic acids of amino acids, fatty acids, they're pretty much always going to be in the deprotonated form. And because we're in basic conditions, it's going to be deprotonated. So I'm actually going to highlight this bond between the O and the H. Why don't we reuse this methoxide that we formed? We could also use a hydroxide, any base, right? You can use a hydroxide, a methoxide. I'm going to use this methoxide right here. That then forms what's called butanoate, which is the conjugate base of butanoic acid. So that's what we actually form. So make sure you include this last step. And notice that I showed this not as a reversible arrow, but as a straight arrow, because this is dang near irreversible in basic conditions. This is going to be heavily, by many orders of magnitude favored over the protonated form in basic conditions. So this is what we get. That's the basic hydrolysis of methyl butanoate, giving you butanoate. If you wanted to get butanoic acid, you'd have to introduce an acid and protonate it. Okay, so now we're basically doing the opposite. Let's make methyl, well, the same kind of principle, different molecule. We have benzoic acid. We want to make methyl benzoate, right? Using a Fischer esterification. Now this is going to be a little bit more of a lengthy mechanism. So if you remember from lab, you guys did the distillation of, well, you did the synthesis of methyl salicylate, which you did using a distillation apparatus. And what that looked like was this. Kind of similar to this, actually. Right, so you had a benzoic acid group. Right? So this is salicylic acid. If you think about the synthesis of aspirin, like we did freshman year in Gen Chem, you reacted this with acetic anhydride. which now you should know when you react this with acetic anhydride, this is going to be the more reactive center, this alcohol. That's then going to make an O-acetyl group here. That is acetyl or acetyl salicylic acid or acetyl salicylic acid, which is the main ingredient in aspirin. And what y'all did in lab is you reacted this with methanol and you heated it up. And what that did is you formed methyl benzoate. Methyl benzoate, right, boiling point somewhere in the hundreds, and that's why you distilled it. Because when you formed it, you then vaporized it and it condensed in your condenser and you were able to isolate the liquid. This is the same thing here, right? We're basically doing the same thing just with benzoic acid. So let's draw the mechanism. So proton, right? Whenever you have carbonyl mechanisms of proton, pretty common theme, right? You're almost always going to protonate that first. So let's do that. I'm going to draw these lone pairs as lines. Just getting a little too lazy to draw the whole thing. But make sure you draw your formal charges. Positive charge right here. Don't forget your formal charges whenever there are non-neutral formal charges. And so the next step is going to be, right, what we did here, right? We've seen before, when we have an oxonium ion, that stuff's positive charge right here, that renders this carbon more electrophilic. So that then activates this for attack. So we can then have methanol come in, as we see right here. CH3OH, lone pair. Right, two arrow reaction here, or two arrow step here. And what that forms looks like this. OH, OH, lone pair plus. I'm just going to draw a methyl group there for the CH3. And we also made an OH here. So we have two OHs. Okay? So obviously, what's next? Well, we have a positively charged oxygen with a proton. That's a very acidic proton. We're going to take that away next. Let's use a base to do that. Why don't we use methanol as a base? Right? So CH3OH. What that then gives you is the next intermediate. Okay? So let's think about logically, right? Okay, where do we go from here? Okay? We want to get from this to, well, obviously, you know, when you do a Fischer esterification, you should know, right? Carboxylic acid plus alcohol, you make the corresponding, where the R group comes from the alcohol, you make R benzoate. So the R group from methanol is methyl. We're going to make methyl benzoate. That's what we're trying to make. So how do we get there from here? Obviously, we're going to have to kick off one of these OH groups, and we're going to have to reform a carbonyl, right, bonded to this methoxy group. How can we do that? How can we kick off one of these OH groups? Well, we know that OH is not a very good leaving group, with the exception of the aldol condensation step. But other than that, OH is never really going to be a good leaving group. What we're going to do, let's make it a good leaving group. We've seen it be made a good leaving group before, and the way we do that is by protonating it. So we can pick any of them. Let's pick this OH. Let's protonate it. Okay. That'll give you this. Positive charge now on that oxygen. Now it's a good leaving group. So now what we can have is that not from the methoxy, but from the hydroxy, lone pair kicks down, forms a double bond, kicks off the water. So we lose water as a leaving group. let that come into focus. That's an H2O. What that then forms is this, which means we're one step away from here. What do we need? We need to take away this proton. How do we do that? We use a base. And I'm drawing reversible arrows, but really these steps with a very acidic proton, they're irreversible. So you can draw an irreversible arrow here, but it is what it is. So I'll use methanol as a base. Important thing is that you can draw the mechanism overall. And that then gives you this successfully methyl benzoate. So that's the mechanism. Zoom that out a little bit. So, okay. Right, so next page, we have a synthesis pathway. And so let's go through it. We have a Grignard reagent. This is going to be allyl Grignard. Allyl because the carbon bonded to MGBR is allylic to this group right here. This is an allyl substituent. As opposed to a vinyl substituent, where if the double bond was like directly right here. React it with carbon dioxide, H plus H2O. Sounds scary. Okay, what does carbon dioxide do? Well, let's remember the structure of carbon dioxide, right? Carbon dioxide looks like this. Maybe hard to see, but that's C double bond O, C double bond O. Or C double bond O, double bond O, right? It's linear, right? sp hybridized. And we know that, I mean, that's not going to be immune. It's not going to be immune to nucleophilic attack. We know Grignard's a very good nucleophile. We can nucleophilically attack this. What does that form? A carboxylate. Let's draw it. And notice we add an additional carbon from this carbon dioxide. That forms a carboxylate. Protic workup will protonate it. You get a carboxylic acid. You react to carboxylic acid with thionyl chloride, SOCl2. That's thionyl chloride. That forms an acid chloride. If you react it with PBr3, right, phosphorus tribromide, that will give you an alkyl or an acid bromide. An acid chloride, the corresponding acid chloride looks like this. Why is this relevant? Because this is a pretty reactive carboxylic acid derivative. So now this step right here, right, don't be freaked out. This is, I believe, tri-T-butoxy, right? So tri because there's three, T-butoxy because you have three OT butyl groups. So tri-T-butoxy, lithium aluminum hydride, right? And followed by protic workup. Basically what this does, the only thing you need to know here when you see this big gigantic reagent is that you're going to go from the acid halide to the corresponding aldehyde. So you're basically going to cut off the Cl bond and you're going to form the aldehyde. So the aldehyde that corresponds, you simply just cut off the halide, replace it with a hydrogen, and that looks like this. Ignore the not so great looking slants right there. That's what we get. Alternatively, let's say we wanted to get the aldehyde. To use something a little more familiar, we know that esters reacted with D-ball, right? D-I-B-A-L, that is diisobutyl aluminum hydride, which we've seen before. That reacts with esters to give you the corresponding aldehyde. So alternatively, we could have done this. We could have reacted this with any alcohol. Let's do methanol. So we can do methanol. Obviously, right, we just went over the mechanism. It needs to be acid catalyzed. Why? Look at the mechanism. It needs an acid. That would then give you the corresponding methyl ester. React that with D-ball, and that'll give you the same aldehyde. So either way, these are the two ways you can do it. I'd be a little more concerned with the D-ball for your exam. This is very much not likely to show up, but it's just there for your information. We then react this with here. I believe this is called an ylide, if I remember right. Looks like that. Kind of an odd name. It's a Wittig reagent, right? Wittig, right? W-I-T-T-I-G, but you pronounce the W like a V. And this is going to react with the carbonyls, right? And basically, when you talk about Wittig reagents, right, you have a carbonyl, you have a Wittig reagent. Okay, what are you going to do? Well, we can think mechanistically, right? You basically have your R group, you have your C, lone pair, negative charge, right, bonded to P, pH3, positive charge, mechanistically. That's what we have, right? And then the next step, we have this. Oh, wait, whoops. This should be a single bond. This will be an oxygen. Bonded to an R. What is this R group? Well, this R group is basically the rest of the cyclohexyl group, right? So really, I should say there's two R's where each side is the entire cyclohexyl group. And just for clarity, why don't I draw it? That's the cyclohexane right there, right? Now what happens next? Well, this happens next. We know that oxygen is going to be more electronegative negative than carbon. We're going to form an oxyphosphatane there. We know that carbon is more electronegative negative than phosphorus. These electrons are going to move here. Think about what that forms. That's going to form this. Let's count our carbons. Right, we go here. Okay. So here, here, and then we go to the cyclohexane ring. Right? Yep. So that's what we get. Alternatively, whenever you have a carbonyl, cover up your oxygen and basically stick on whatever Wittig alkyl group is on here. So in this case, alkyl halide. But mechanistically, this shows you the mechanism. And that's why it helps to know mechanisms, because when you know the mechanisms, it'll never fail you. And you form the oxyphosphatane, or pH. And these are all phenyl groups as a side product. But this is the main outcome. All right, a little bit of naming. So let's name them. We have esters, right? Make sure you have your notes on these, right? And I'll free up a little bit of room here. Esters, alkyl, alkanoate, right? So our alkyl group here is isopropyl. So we're going to do a lowercase isopropyl, space, right? No dashes. There's a space. Alkanoate. What is the alkanoate? Look at the parent chain. This is a propanoate chain because there's 3 carbons. This is carbon number 1. This is number 2. This is number 3. There's a phenyl ring on carbon number 3. So it's going to be isopropyl space 3-phenyl, no space, propanoate. That's what we get. All right. Let's look at the next one. This is going to be a nitrile. We know that nitrile carbons are involved in the numbering, and they always take carbon number 1. We also have an alkene functionality in here. So notice, usually with naming, when it comes to numbering, right, and figuring out the parent chain, it's all about what has the longest chain. Well, we know that when there's double bonds or triple bonds, that rule goes out the window. Whenever there's a double bond or a triple bond, all of a sudden it no longer becomes about the longest chain period. It becomes about the longest chain that involves that double or triple bond. So in this case, we have to consider this as our parent chain because it includes a double bond. We know our name is going to end in nitrile. Okay, let's count how many carbons. We have 1, 2, 3, 4, 5 and 6. Okay. We have an ethyl group on carbon 4. We have a 5-ene, right? And so let's name it. It's going to be 4-ethyl dash 5-hexene nitrile. And this should be NITRILE. So notice the 4-ethyl, 5-hexene nitrile. So it's like, oh, well, why don't you have another number? It's because you only need the 5 before the hexene nitrile. It's assumed that in the nitrile, carbon number 1 is the cyanocarbon. That's assumed already. The 5-hexene tells you that there's an alkene, there's a double bond starting on carbon number 5 and 4-ethyl substituent. 4-ethyl, 5-hexene nitrile. And again, make sure you review your notes on these. All right, there's some good practice here, but make sure you review your notes. Right, naming just takes practice. So let's go through the next one. This is going to be an acid halide. And when it comes to acid halides, you have alkanoyl, right? So alkan, so OYL, alkanoyl. I can't speak right now. Alkanoyl chloride, or bromide if it's an acid bromide. That's the IUPAC name. Let's go through it. Let's look at our parent chain. We don't have any weird double bonds or anything like that. This is our parent chain. This is carbon number 1, 2, 3, 4, 5, 6. 6 carbons. It's going to be a hexanoyl chloride. 1, 2, 3, 4, 5, 5. So it's going to be 3, 5, 5, tri-methyl hexanoyl, no space right here, but we have a space right here, hexanoyl chloride. All right, let's get into the amide. So amides, we know our parent chain is going to be the amide. All right, our principal functionality is the amide, so the name will end in amide. And so the way it works, you have your N substituent, so you'll have N something. So in this case, it's N-ethyl, right? And then you have your methoxy substituent. And you have 1, 2, 3, 4 butanamide. So when it comes to, like, obviously here, like you have 4-ethyl, 5-hexene. You have 3, 5, 5 trimethyl. You have numbers referring to the positions of these substituents. Here you'll have an N-ethyl. Now, as far as alphabetical, alphabet goes when it comes to naming order, the priority is the same. It's all about what comes first in the alphabet. Treat the N just like it's any other number, like it's a 3 or a 4. It's treated like another number. It's not like the N always comes first. In this case, it will come first. Why? This is a methoxy substituent, which starts with an M. This is an ethyl substituent, which starts with an E. What becomes first in the alphabet? E. So in this case, we have N-ethyl, right? And then we go to the butanamide chain. This is carbon number 1, 2, 3, 3 methoxy, butanamide, N-ethyl, 3 butoxy, butanamide. Let's now formulate the structures. So these names can be scary, but I think these are your more soft-toss type of questions. Just take it from the right to the left. Let's start with the parent chain. And that's always told at the end of the name. Pentanoic acid. That tells you we're going to have a pentanoic acid. Let's go ahead and draw that. But notice the EN. 2-pentanoate. That means we have a double bond starting at carbon number 2. This is carbon number 1. This is carbon number 2. Double bond between carbons 2 and 3. We have a 3-phenyl. Okay. 3-phenyl. 4-oxo. Oxo means carbon double bond. All right. Could also be an aldehyde in this case. It's known that it's a ketone just because there's 5 carbons and carbon number 4 bears the oxo. Let's do this one. Methyl, 5-methyl, 2,4-hexadienoate. Okay, what do we have here? What pattern? We have an alkyl, methyl, alkanoate, right, hexadienoate. That tells me we have an ester. So let's draw it. We have a hexadienoate. So diene 2,4, that means we're going to have two alkenes in here. We're going to have some sort of conjugate. But let's draw, it's hexa, so we have 6 carbons. Ester, right, we have a methyl ester. We know that from the methyl. Let's focus on this. 2,4 hexadienoate, that means on carbons 2, 3, carbon 4, we have the diene. 5 methyl, so 1, 2, 3, 4, 5 methyl. And there you have it. So start from the end of the word or end of the name and work backwards. Look at the parent chain and stick on your substituents from there. We have a methyl ester, okay, from a hexadienoate. So, okay, we have some sort of hex. So 1, 2, 3, 4, 5, 6. Methyl ester, 2,4 hexadienoate. That means on carbons 2, carbon 4, right? So between 2 and 3, between 4 and 5, we have double bonds. We have on carbon number 5 of the alkanoate group, right? We have a methyl group. So this is what we have. 5-methyl, or methyl 5-methyl 2,4 hexadienoate. Now, when it comes to anhydrides, these are relatively straightforward. Key is it's all alphabetical. So we have acetic, that means one side is acetic. Could also be ethanoic, right? But a lot of times with ethanoic acid, we use acetic acid as a common name. We have the other side of the anhydride here, and it's a butenoic. So it tells me there's 4 carbons on the other side, and it's got a 3-ethyl, 3-butenoic. So it's like, okay, why is that not 1, 2, 3, 4, 5, 6, right? We could have even more carbons come from here. 1, 2, 3. 1, 2, 3, 4, 5. Why is this not the parent chain? Remember what I said earlier. Whenever there's double bonds or triple bonds, that rule goes out the window, and all of a sudden, it doesn't just become about the longest parent chain period. It becomes about the longest carbon chain bearing the double bond, which in this case is this one. Hence, we have a butenoic acid, 3-butene, right, on carbon number 3. Okay. We don't put the double bond here because then that would be a 5-member chain. And so that wouldn't work. So it specifically has to go right here. 3-ethyl, 3-butenoic anhydride. And as far as anhydrides go, you basically have alkanoic, anhydride, right? As far as what comes first, it's all alphabetical. So acetic comes first in the alphabet. The next thing is the first substituent that shows up alphabetically in your second parent carboxylate group. So in this case, it's not the butenoic, it's not the B you're looking at. You're looking at the E from the ethyl. So that ethyl substituent comes first. You compare the E to the A. Okay, well, A obviously comes first in the alphabet, so hence we name this acetic 3-ethyl 3-butenoic anhydride as opposed to 3-ethyl 3-butenoic acetic anhydride, right? So first in the alphabet first, second in the alphabet goes second. So cyclohexyl 4-T-butyl 2,6-dichlorobenzoate. Let's draw it. We have a benzoate. Let's draw that first. We have a cyclohexyl. Right. There's no substituents on the cyclohexyl. Right. We have 4-T-butyl. So that's on the benzene ring. That's in the para position. 2,6-dichloro. So 1, 2, 3, 4, 5, 6. And there you have it. Cyclohexyl. Right. 4-T-butyl, 2,6-dichlorobenzoate. That's the ester there. All right. Last question. Okay. We'll have a synthesis problem. All right. So this problem looks pretty tough, doesn't it? So let's break it down. Let's look at the product and let's kind of see what do we know. And let's also do some cross-referencing to the reagent. So we're starting with toluene, right? That's the methylbenzene. And we want to get this molecule right here. And I don't even really know exactly the name of it, but besides the point. You don't need to know it either. You just got to know how to make it. So I see a methyl group right here. Okay. There's still stuff here. We have this whole big group right here that we added. Okay, it's got an alkene. That's interesting, right? We had all that ROMP stuff, ring opening metatheses, ring closing metatheses before. Perhaps that might come into play here. We have a hydroxy, so we have a tertiary alcohol. Okay. We have a bromine right here. Okay, that's interesting. That's on the benzene directly, so we definitely have to do an electrophilic aromatic substitution, specifically a bromination with Br2, FeBr3. But notice the bromine is meta, to this carbon right here, bearing the methyl substituent and all this substituent stuff in the product, which means we had to have had, obviously the methyl right now is orthopara directing. That's not going to stick the bromine in the meta position. So it had to have been converted to some sort of deactivating group somehow to get the bromine there. So let's think about it. How can we make this a deactivating group? Well, I can tell you the first thing I think of when I see a methyl. Let this come into focus. So I would say, let's oxidize it and form benzoic acid. And let's just think, if we do that, we can then brominate, install the bromine in the meta position. Okay, we have this group right here. What I would say is we can probably, what we'll have is the benzoic acid, right? We want to then get a primary alcohol. Well, we know if we can make an ester maybe, which we can make an ester from a benzoic acid or any carboxylic acid via Fischer esterification, we can then make an ester, and then we can install two equivalent R groups, forming then a tertiary alcohol from a primary, or forming a tertiary alcohol from an ester by reacting an ester with a Grignard reagent. And we can maybe do some RCM to close this up. But let's take it one step at a time. I just want to get through the thought process first. Let's oxidize this thing. Let's do sodium dichromate in acidic conditions. So let's maybe add some sulfuric acid, some water, right? Aqueous sulfuric acid to provide for sodium dichromate in acidic conditions. That's a strong oxidizing agent. That's going to oxidize this methyl group all the way to the carboxylic acid. So we'll now get benzoic acid. All right. Now we can brominate. Let's do that. You could make the ester at this step right here, but let's just go ahead and brominate. Let's do Br2. FeBr3, don't forget your Lewis acid. All right, go back to chapter 18 if you want to review the mechanism of this. Here you just have to know what the outcome is. Br. That's what we get. We get meta-bromo-benzoic acid. Now we can esterify. We can make any ester. We can make a propyl ester, an ethyl ester, a methyl ester. Let's just make a methyl ester. Let's keep it simple. We use methanol, catalytic acid. That'll make the 3-bromo or meta-bromo, it'll be methyl 3-bromo benzoate or meta-bromo benzoate. You think about the name. To OME for O-methyl. Okay, let's look right here. Notice what we have. Notice this group right here. How can we make this? My thought with the alkene is, if we start with this circle, we need to use an RCM. And my thought process is we use these guys. Because when you do RCM with this, what you're going to get is you're going to cut this. You're going to link these together and form a double bond. You're going to form ethylene as a byproduct. And what you ultimately get I say really the pentagon, but that's what you get. Right? So that means we need to install this allyl substituent. Right? Specifically, we need 2 equivalents of that. Well, why is that convenient? Because when you react a Grignard, 2 equivalents of it, with an ester, you install 2 equivalents of whatever alkyl group is on that Grignard onto the ester. You reduce it all the way to the tertiary alcohol, and you have your 2 equivalent alkyl groups. Let's do that. If you remember back from chapter 12. So here, we can do allyl Grignard. 1. So 2 equivalents of that. Don't forget your product workup. All right. These guys are very basic. You worked with them in lab, right? Remember the synthesis of triphenylmethanol, right? And so you have to use some acid to work it up. Remember how it probably bubbled pretty violently in the reaction vial? That's because Grignards are very basic, and when you're reacting with acid, it reacts pretty violently. That's why you want to slowly drip the acid in until all the Grignard reacts, and all of a sudden it's not so violent anymore. But we need a product workup, right? And what that'll give you, is this. Right? We're going to do one last step here. And you don't have to even know the reagent. It's simply RCM, standing for ring closing metathesis. And like I said, we're going to cut these guys. We're going to form a double bond, 5-membered ring here, taking out ethylene as a byproduct. And this is what we're going to get. Make sure you review chapter 19, review those RCMs, review those RMPs. I know they can be a little tricky, but they are very important because they will show up on the exam as they're showing up here. And notice, this and this is the same thing. So we successfully perform that synthesis. All right, so that's it for chapter 20. Let me know if you have any questions. Good luck on the exam.